So this brings us to our, well, the second tutorial, which is now already a bit more on actually implementing code inside, well, in Trilinos. And well, those slides are somehow from well, based on the lecture that I gave, and it was actually, well, like going through all like the things in detail. It took actually quite some time. So I hope I can give you a very brief introduction to those like concepts here, and then hopefully this is enough for you to get started with the exercise that will follow. And I mean, this first part, well, it's so we have two parts now about using Trilinos and application codes. And well, what does that mean? Here in the first part, we will be talking about the paralinear algebra interfaces in Trilinos, or packages. And as Matthias well, discussed earlier, there are basically two stacks of software in Trilinos. One is based on Tpetra, and the newer one, which is based on Tpetra. And since all the algorithms are really basically built on top of this, let's say, these linear algebra objects, it's really like that's the most essential thing to know to get started with Trilinos. So this is here just, well, again, some disclaimers. So I will really focus on discussing Tpetra, and I will discuss mostly focus on MPI parallelization. So as Matthias already discussed before, there's also in Tpetra, using this COCOS programming model, there's the way or the option of using additional node level parallelization, which is typically referred to MPI plus X. So you have on the, let's say, between the processes, you have MPI, or between the nodes, and then on the nodes you do some other parallelization concept on typically based on shared memory. So that could be well, something, let's say, with P threads or OpenMP, or even like some CUDA if you have GPUs available. But this is out of the scope of this this tutorial, and there will be also a talk tomorrow by Luke about COCOS, so you will hear more about that. And because this is really, well, this is, as I said, it's based on some lecture. What I would also encourage everyone who basically gets started with Trilinos, and well, while going through the breakout rooms before, I noticed there's hardly anyone here who has not worked with Trilinos at all. But I would suggest that before you actually get started, you also, well, look a little bit into the Tefos package, because this really gives you a lot of functionalities that you are maybe also already know from other, let's say, from other programming languages, other libraries, which are very useful for you. For example, there is this RCP, so that's a reference counting pointer, which is basically for it's a smart pointer, and that makes sure, for example, that you it prevents you from well, from memory leaks and so on. So it helps a lot with those things. There are parameter lists if you don't just, well, hand one parameter to your function or your code, but really like a large list of parameters, which can be the case, for example, for complex solvers like multi-level solvers, multigrid, or DD. Well, then there's also some wrappers for MPI communicators and so on. There's wrappers for BLAS and LAPACK routines. So I think it's really worth looking into this and getting used, when you use Trilinos, getting used well, starting to use all those things, because they will really make your life easier. The most important classes or objects in Tpetra that I'm not sure if we will not discuss all of them really in detail, but I think we'll cover most of this. First of all, both in Tpetra and Tpetra, there is like this concept where, well, it's always called maps, and these map objects basically just determine your parallel distribution of any parallel distributed linear algebra objects that you could have. So basically, this is, and that is most of the part actually of this, these slides is to describe what it means to have a map and how a map helps you to parallel distribute some objects. Then there are different types of these parallelly distributed objects that you could deal with. Like the easiest case is just a single vector, which is a Tpetra vector here. And then there is a multi-vector, which is just, kind of, you could say it's a tall, skinny matrix, or you can just say it's a collection of parallelly distributed vectors with the same distribution, so also the same length. And then there are a couple of objects or classes which are generally referred to something like an operator, so something that you can actually apply to a vector. And that is, there are these two abstract classes. One is a Tpetra operator, which is just like the general class for some, like an operator that can be applied to a vector. So this, and then there is one, let's say one derived class from that, but still abstract, is the row matrix. So that is basically, it's a matrix that is distributed according to the rows. And but it doesn't have a specific implementation for the data format that you have to store each of the individual rows. And then, the specific implementation that you will mostly use is a CRS matrix. And that is really, a compressed row storage format that is used to store each of the rows of the parallel distributed matrix. And then there are also some, like these import-export objects, and we will, they are in the slides, but I don't think that we will really have the time to go into this in detail. But I will, depending on the time, I might cover it, or you can also take a look at it later. But this is really, if you have, let's say, a vector of some length or matrix or whatever, and you would like to change the parallel distribution of that, then you have these Tpetra import and export objects that can actually do this automatically for you. And I would, let's first discuss the concept, this map concept. And for that, as I said, I mean, all these, if you look at the vector and see as like a column vector, then you could say that all the parallel linear algebra objects here are distributed based on the rows. And so, for example, you could have a vector V, as you can see here, or matrix. And then, you would like to, if you have two processes, for example, you would like to distribute in the way that I showed here. So you want the first, third, and fifth row on one rank or one process, and the other two on another one. And now the question is, how can you do that? For example, there are other, other than Trilinos, other parallel or let's say high performance packages, which always assume something like a linear distribution. So you always have like the first rows are on one process, and the last ones are on the second one. Or if you have more, then it will be kind of, they try to equally distribute it according to that. But of course, here you have, maybe you want to have your own way of distributing this. And the question is, how can you do that with this map concept? And of course, if you look at this, basically everything that is blue will now be stored on the one rank, and everything that is red will be stored on the other rank. And that is basically what you just see here. So this is really just, let's say, just in terms of the data, so of the entries. This is everything that you have to store locally in order to do that. But now, of course, this this gives us some kind of a whatever problem, because there is no unique or no clear way of assembling the original matrix if you locally only store this information, right? Because as you maybe remember, the first row on rank on process 0 was also the first row of the global matrix, but the second row was the third row of the global matrix, for example, or vector. So that is really information that if you would only store the entries, that is something that is, that is lost. And you cannot really, not even logically, no way you can, reconstruct or reassemble the matrices and vectors, the global ones from these local data. So something that you additionally have to store, and here I start on the right with I have 2 additional index vectors basically, and they tell you the local index. And here, well, because we're dealing with C or C++, we start with the 0. So the 0th row on rank 0 is also the 0th row of the global matrix. And the second, well, and then the first, let's say the one with index 1, so the second row here corresponds to the 3rd row in the global matrix, which has then the index 2, and so on. So this is the additional information that you need in order to recover the global matrix from this local information. And then this is, you can easily see, right? So if you see it in that way, you have stored here a local vector, local part of the vector. At the same time, you have stored a local part of a matrix. And then if you add these index sets, basically you can, well, have can really say, okay, what part of the global matrix are these local entries that I stored. The same you can do on the other rank. And then if you could this V0 and V1 stored in that way, you can easily combine them and get back the original matrix, as you can see here. And I mean, this flexibility of really defining yourself how the parallel distributed linear algebra objects, how they are distributed among the processes, this is basically only possible due to this index mappings or index sets. And basically that is exactly what is called, or what we call a Tpetra map here, right? So this is basically, it's an index mapping from local to global indices. Of course, there are also links always to the corresponding website of the documentation, so you might want to take a look at that as well. Now, if you think about, for example, finite element simulation, a very typical case is that everything that is locally next to each other, you also want to maybe have on the same rank. So maybe if you have such a grid here, such a mesh, you might want to have like this lower rectangular block to be on process 0. You want to have maybe this one on process 2, this on process 3, and this on process 4. So basically, and this is already not compatible with just using a linear mapping, because then you would just have like the first few rows here in this mesh. If you have a lexicographical ordering, you would only have the first complete rows on the one rank, and then the next row maybe on the other rank, and so on. So and because of that, basically, in order to split this again, what you need here, I always have in red the global index and in blue the local index. So if you would want to do such a parallel finite element simulation, for instance, basically what you need is a map that always tells you for the local blue index the corresponding global red index, right? And then if you have that, you can, for example, store the corresponding finite element vector or matrix in the way that I described before. Now, let's go a little bit specifically into some of these objects. So as I said, the first example that we have here is a parallel distributed vector, so a Tpetra vector. And basically, well, what is the data that is stored if you create a Tpetra vector? The most essential parts are really the local portion of the vectors. So that is basically really just the entries, right? So we had that before, this V, X, and Z, and W, Y on the 2 ranks. And additionally, as I said, to recover the global object, we need those local to global mappings, here M0 and M1. And those are basically, that is just the Tpetra map. And then, as you can see, if you want to construct a new vector, basically everything that you need, there are some optional arguments, but everything that you need is just to specify the map. Because the map, for instance, it also gives you already the information about how many local indices you have and how many global indices there are. So once you have that for a vector, you don't even have to specify how long the vector is, because that is already given due to the local global index mapping. So that's really, well, so it's relatively, once you know how your index mapping is, for example, for the finite element case, you can easily just generate some vector, right? With the initialized with 0, so doesn't have any, well, useful information yet, but just to construct the object is really simple. As I said, something that is actually also used very often, this is actually also in Trilinos, is actually the base class even. So the vector is derived from the multivector, is Tpetra multivector, and the Tpetra multivector is just a collection of multiple vectors which all have the same parallel distribution. So you see you have like basically you can see it as a matrix, and each of the row of this matrix is it's parallel distributed, but you don't want to use that to store any matrix, for example, in finite elements, because this is of course a dense matrix, right? So you have because each row of this is a vector, you don't have any, well, you don't have any sparsity. Every element of this matrix is stored, and there are a couple reasons why you would want to store something like that. Either you really have like a skinny dense matrix, maybe a very tall skinny matrix, or the other option is really maybe you want to solve a lot of linear equation systems or multiple with the same matrix but different right hand side vectors, and then you also get of course multiple solution vectors. And if you want to do that, you would do that with a multivector. Of course, you can also do a multivector with just one vector, and that is then just basically just a standard vector. Now, the more interesting object, I would say, and that will also show you the high level of complexity that is introduced by having all those maps, is the Tpetra CRS metric. So really a specific type of a sparse matrix that is distributed in parallel or according to some map again. So the general concept, first of all, is exactly the same as before for the vectors. So we have basically we store the local portions of the matrix. So all the data, all the entries that belong to one of the ranks, one of the processes. And again, here we store the local to global mapping for the row indices. So that is again just the Tpetra map. Because this is also a sparse matrix, we, for a minimal way to constructing an empty sparse matrix here, we also need to specify at least some information about how many entries per row you will have. And this is just here, an upper bound. So here you basically say, well, we have maybe, I don't know, 1, 2, 3, 4, 5 numbers are maximum per row. So that tells Trilinos how many, let's say, how much memory to allocate. But of course, there are also other options where you specifically say how many entries you will have in each specific row, right? So this is just the most simple case. For example, here we would have a maximum of 3 entries per row. And then we additionally have this row map. But now everything will become not much more, but more difficult for the setting of a matrix. Because, we have what we discussed so far is that we have a parallel distribution of the rows. Now, on the other hand, by looking at such a parallel distributed matrix, there's actually, this is now a bit more complicated example or larger example for with 3 processes for a distribution of the rows. But of course, you could also, and that we will see why this is relevant on one of the following slides. Of course, the columns also have some parallel distribution, and that is actually in practice usually not the same as for the rows. Well, there are specific cases. If you have a block diagonal matrix, you might have the same, right? If you have a block diagonal matrix, it could be that the row and the column map are the same, but in general for a matrix they will not be the same. So for example, if this is the row map, right? So the parallel distribution of the rows. Then if you look at this, like here on the bottom, this would be the corresponding or one corresponding way to have a, or to specify the parallel mapping of the columns, right? So if you say the first two rows are owned by process 0, that means that at least the first 3 columns also have to be owned by the corresponding process, because if it would not, then we would, well, miss one of those entries. And then, well, you see the same for process 1. If we want to have those rows on the process, we will also have corresponding, well, a larger amount of columns, here in this case 4 columns assigned to process 1, and so on. Well, this is also in some way relevant for a matrix, because the rows are of course important because you have some local to global mapping there, but also for the columns you need to have something like a local to global mapping if you want to store this, right? If you want to recover the global matrix from the local one, you might also need something like a local to global mapping for the columns. And that introduces or induces this column map. And what you see now, of course, here the row map, and that is also kind of, well, the most typical case is that the rows are actually distributed in a unique way. But very often then the columns are not uniquely distributed, as you can see for this example here. Right, so they are generally not unique. That means that there are columns which are, well, assigned to more than one process. Okay, so that's, let's say, so far, and that is everything that we need to know in order to fill the matrix with values. Okay, so we first of all, we have created the matrix, and we, well, first of all, an empty matrix, for example, using this constructor here, right? So, and at that point, we only have some memory allocation, but we don't have any entries in the matrix yet. And there are, if you look into the Trilinos documentation, you will find that there is a larger set of functions that you can use in order to add values to your to this empty matrix. And here I will basically show you, well, 2 examples, but there are more, but this is kind of a bit out of the scope here. Well, also due to time reasons, not possible to add everything to this short tutorial. So first of all, what basically the 2 most commonly used examples for adding values to your matrix are insert local and insert global values. And the most simple case is actually insert global values. And I will just discuss in a second why this is the case. But I wanted to explain you both those differences, because that also again tells you or relates to those maps that we had before. Okay, so first of all, something that, as I mentioned before, so we're talking about sparse matrices. So those functions, insert local values and insert global values, use for each row, right? So you go a row by a time, row by row. And so you can only, at one call, only add multiple. You can add 1, but you can also add multiple values, but only to one row of the matrix. And then, so this is the index of the row, and then you specify the columns and the values in CSR matrix format, right? But just for this one row. Now, of course, if you think about a finite element assembly, you might, well, add to multiple entries to, or you want to add up multiple values in one entry of the matrix. And that is fine if you do, even if you do insert local or insert global values, because if you insert twice at the same location in your matrix, those will be added up later. So this is all fine, especially for, let's say, a standard assembly from some discretization method. This is really what you want to do. But there is really, well, a significant or important difference between those 2 options that you have. So let's start maybe with the insert local values. So it is called insert local values because, well, the values do not change, but the things that are local are all the indices. So if you use insert local values, you will add entries to your matrix only using local indices. That means both a local row index and local column indices. Now the problem is, or well, it's not a problem, but if you want to use local matrix indices, you always have to know the local to global map, right? Because otherwise there's no meaning of a local index if you don't know what the corresponding global index is. And this means that if you do this insert local values, the matrix already has to know the information, or already has to know what the row map, so the local to global mapping for the rows, as well as the local to global mapping for the columns is. So this has to be the case. And if you do that, because you use local indices, you also cannot, well, you cannot do any off-process assembly. So if there is a row that is not on the process where you call this function, you cannot add any values to a process that is not on the process that is calling, because there is no, well, there's no local index then, right, for this global row or global column. And then there's the second example, insert global values, and that makes your life much simpler actually, but it's also, well, maybe the less efficient one for a certain reason. So if you do insert global values, all the indices that you use are global indices. So for the row and for the column numbers, you use global indices. And well, this has different advantages. One advantage is that you can actually also, well, if you're on process 0, you can also add some entries to a row that is not owned by process 0. Well, so then that will actually, Trilinos will take care of, or Tpetra will take care of communicating that at some point. I will discuss that in a second. And it also has an advantage because, well, we always need to know the distribution of the rows for a matrix. That is because we have seen that's like the minimum that we have to specify when we construct the matrix. But it's not, as you see in the constructor, there was no need to specify a column matrix. And so if you don't specify a column matrix map there, and then you use insert global values, what Trilinos will actually do for you is by let's say all those column indices that you add using insert global values, it will automatically create a column map for you at some point, right? So that is why you're like really knowing the row distribution is really the minimum that you need to know. Everything else can be taken care of automatically. Of course, you can imagine that, well, creating such a map is causing some additional work, of course. And also communicating entries is, of course, well, some additional work that has to be done at some point by Trilinos. So it's more simple in that sense to use directly always deal with global values, but maybe it can be a little bit less efficient here. Well, and I always said, well, if you don't do certain things, at some point Trilinos will communicate this, or at some point it will create such a map. And this is actually done when you call the method fill complete, which basically tells Tpetra that you are finished with adding any entries to your matrix. And then a couple of things will happen. Most importantly, those rows that are not owned by the process will be communicate to the actually owning MPI rank. Then the final CSR format of the matrix will be computed. So, well, which entries have non-zero values, and then you will add up those which belong to the same position in the matrix. And then you will also have this, this transformation of global indices into local indices, especially in the case that you use global indices for assembly. And then also this new column map will maybe build. Okay. And then you always have to call this fill compute before you do anything else with this matrix, right? For example, multiply it with a vector. Of course, you can later, then there's some things that you might want to know. For example, you get a matrix from somewhere, or you want to know the distribution of the rows and the columns. You can easily get that here. You can actually also, well, once you said, I'm finished with adding values to your matrix, you can use it. If you later want to again add some values, you can do something like resume fill. So you can add more values if you want. And then there are also, as I mentioned, some other functions that you can use. If you, for example, use this resume fill, you can also really replace one value in the matrix by another one, or something into this value later with those functions. But it's really a little bit out of the scope here, and you might just want to look at the documentation in case you're interested in those. Now, this is really more or less the last thing that I want to mention. I know I'm a little bit over time, but I hope it's still okay. Is one important example or something that you might want to do with the matrix, namely multiplying it with a vector. And well, you can apply any Tpetra operator, so any object that is an operator can be applied to a vector. And especially one example is such a matrix. And well, this concept of the maps actually allows for a very, very general situation that is basically shown below here. So Trilinos can deal with the case that you have a matrix that is somehow parallel distributed, and you apply the matrix to a vector that has a different distribution, and the resulting vector also has a different distribution. So basically, well, everything, like each step that you do changes the distribution kind of the vectors. And this is actually possible, but you need additional maps in this case. So this is not used in this example. But it's just to give you some feeling for like the possibilities that you have when using this concept. So the row map tells you the distribution of the rows. The column map tells you the distribution of the columns. And then you can also have a domain map. Domain map means that's in the sense of the domain of a linear map from a map from linear algebra. Basically, that would be the distribution of a vector that is applied, the matrix is applied to. And you also have a range map, that is the distribution of a vector that is the result from your matrix vector multiplication. So if you have those two additional maps, you can do this. And then, well, then there will be some stuff going on in the background, some communication, right? Because what you first have to do is you multiply, if you want to multiply this vector with the matrix, you have to communicate all the entries such that you have everything locally there to do the multiplication and summation of entries. And once you're done with this, you also have to, well, redistribute the resulting vector again. So this is performed, and that's the nice thing. If all the maps are, well, if they all fit, all the communications performed automatically. Now the question is, I said you need those two maps, and where do you specify them, right? At the construction, you don't do it. You can specify the domain and range map when you call the fill complete. And then the first entry of the fill complete, the first argument would be the domain map, and the second one would be the range map. Let's say in the default case where you don't specify anything with the fill complete call, it will assume that the range and domain maps are just the column maps of your matrix. And that would mean that the vector you apply to the matrix and the resulting vector also have to have the same distribution as the matrix rows itself. Okay, so that's really the most general case. That's not really what you will not do it in this example or this tutorial, but or in the exercise, but it's something to be aware of, so you can deal with very general situations with this concept. This import and export, I said, because of time, I want to skip this, but basically this is kind of, you have a vector with some distribution and you would like to have a different distribution, same for a matrix. This can be done with this import-export object, so I'll skip this and just come to this, the exercise for this part. This is in the folder for exercise 2. And here really the goal is just to assemble a 1D 1D Poisson equation, more or less. or 1D Laplace operator, the matrix. Some right-hand side, I think we just took a constant vector 1 or something. You can also use a different vector if you want to do a bit more additional stuff. But basically, just assemble a matrix that corresponds to a 1D Laplacian operator with finite elements or finite differences, and then some vector on the right-hand side, and then you solve this with Amesos, so with a direct solver. And let me just, as a last thing, before you start, 1 second. I'm just trying to switch this here. 1 second. So this is, yeah. So I just want to, I think you see this now here. So basically, again, just the last thing. So you basically, this is in the folder exercises. Then there's the folder exercise 2, and they're in the source. Basically, this is now a bit long, like a bit longer code. You have a lot of stuff going on in the beginning, and you can probably just ignore this. There's a lot of things that are defined and so on. You can ignore this and really, well, I think this is the first part actually where you're supposed to add some code. So there's a lot of things defined here to make the code a bit more better readable. So maybe you can first ignore all these definitions and start looking more at specifically at the code after this point here.